Okay, let's look at question number 4 of the applied way. A train of mass mkg moves along a horizontal track at uniform velocity. Rear compartment M, simple mkg of the train detached, and the engine driver is informed after it travels L kilometers. At this moment, driver stops the engine if the resistance to the motion of the train is uniform and proportional to the weight of the train. Show that the distance between the rear compartment and the train is this expression when the both parts become at rest. Power exerted we have to take is constant. Assume that after detachment compartment engine continues with the same tractive force. Right, we'll do case by case. So before detachment we'll do first. Before detachment this goes with uniform velocity. And then the resistance is what? Some proportionality constant K, the weight mg, and tractive force will take as F. Because this is going with uniform velocity, tractive force has to match the resistance. Those are the only forces, so that is first equation we can come up with. Then what happens? Rear compartment deattaches, so now the mass of the train is capital M minus M. The resistance is what? We can use the same capital K proportionality constant because resistance is uniform and proportional to the weight. So uniform means all the conditions remains the same. Even though the mass goes down, all the other conditions remain the same. So proportionality constant is the same. So we can use the same proportionality constant here. Right. So now the resistance is that. And even after the deattachment, they say the tractive force is same. So same capital F. Now this force is greater than this, the resistance. Therefore, now it has acceleration. So let's find the acceleration by applying F equals ma in this direction. So capital F minus this ma. So capital F is the tractive force, this. Let's see what we get. Right. These two terms cancel out. Away. This is wrong. Mass is what? Capital M minus M. Right. So this cancel, this cancel. So you get acceleration is what? K M G over M minus M. Right. This is the train's acceleration after the deattachment. Right. Now what happens? After the deattachment, so speed after deattachment, it goes L kilometers before the engine is stopped. So it was traveling with this initial speed, then it goes L kilometers like this with acceleration a that we found. So we need to find the final speed here. After that, what happens? Engine stops, no? So then it goes with a different deceleration a1 that we need to find and comes to stop. So we need to find these two distance. No, L, we know S1 distance we need to find. Right. So let's see. So let's figure out this one first. This speed, let's say it's v1. So v squared equals u squared plus 2as will apply. So v1 squared is what? U squared plus 2 that acceleration we found, which is what, kmg over capital M minus M L, right? So this is second equation, v1 squared. If we need v1, we can square root it. Now for the second section, this section, what is the only force acting on this? That is the resistance, because engine stopped, no? So what is the acceleration then? Apply F equals ma, apply F equals ma in this direction after the engine stops. So engine stops, engine is cut now. So then the only force is minus k m minus mg, mass is this. So then the acceleration is what? Or the deceleration. So acceleration is minus k g. Right. So then for that section, let's apply v squared equals u squared plus 2as again. So you will get what? 0 v1 squared. V1 squared is what? This one minus 2 kg s1. So then 2 kg s1 is equal to v1 squared, which is u squared plus 2 kg ml over m minus m. So then S1 is equal to what? U squared over 2 kg, 2 kg, 2 kg cancels, ml over capital M minus. Right. So then we can write total distance travel by train is what? L plus S1. Now let's figure out the distance traveled by compartment. So let's take that to be S2. Let's find S2 now. Find S2. So for the compartment, what's the only force? Resistance, kmg. So then let's figure out the acceleration. Apply F equals ma to the compartment in this direction. So minus kmg, ma, m and m cancel. Same deceleration as the train after detachment. And the starting speed was u for both. Right, then apply what? V squared equals u squared plus 2as. Final speed is 0, initial speed is u squared minus 2 kg s2. Then s2 is what? S2 is u squared over 2 kg. Right, so then we can find the distance between these two. Distance between compartment and train is what? Train is L plus S1 minus the distance traveled by the compartment S2. So L plus S1 was what? Number 3 gives us S1, u squared over 2 kg there. Plus ml, this one, minus S2 was u squared over 2 kg. So these two cancel. Simplify. ml minus n, simple ml plus simple ml over m minus m So then we have what we want. So this is the distance between the compartment and the train when they both come to rest. Right. So that is the fourth question in the applied